So, welcome to this lesson about random variables. Today we will talk about one type. We have two types. A random variable can be discrete, but we also have the continuous. So today we will talk about only discrete random variables. But what is a random variable? A random variable makes a correspondence between the result of a random experiment I denote by R dot E. We talked about random experiments when we gave the probability theory, so we already know that a random experiment, we only know the result after the experiment, but before we know the possible results. So the basic correspondence between the result of a random experiment and a real number. So a random variable assumes a value. Let's put here the example of the random experiment throw of two coins. So the possible results are we can get ground, face, ground, and face. And now we can define a random variable. But let us put here the way we denote random variables. We denote random variables by the last big letters of our alphabet. For example, big X, big Y, big Z. And the value assumed by the random variable, we use the small letter. Here, small x, small y, and small z, for example. Sometimes we use the x for any real number, for example, any input in the probability function, for example. So we can use the small x for a value assumed by the random variable big X, or sometimes for all real numbers. But here we will consider the random variable big X number of faces when we throw two coins. So it will be the number of faces when we throw two coins. This random variable can assume three values, 0, 1, or 2. So I will put here small x. So the possible values for this random variable are 0, 1, and 2. But the number 1 has more probability. Why? Because in the random experiment, we can obtain these 4 results, but in two of them, we get one face. So, and for example, we have only one of them with 2 faces and one of them with 0 faces. So now we will define the probability function. So the probability function, the rule is to give to each possible value its probability. So I write here probability function. Probability probability function. We denote the probability function by the small f. And then we put here the name of the random variable. Sometimes if it's implicit, we can drop here the letter of the random variable. Then small f with small x here, if we are talking about the random variable x, and it's equal to what? It's equal to the probability that the random variable big X assumes a value equal to a small x. So here, this small x can be any real number. Okay, we can put any real number as input in the probability function. For example, if I write a small f with the input equal to 1 for the random variable x, so this one here. What is the meaning? The meaning is the probability that the random variable assumes a value equal to 1. So when we know that the probability that x is equal to 1 is the probability of obtaining one face when we throw 2 coins. The probability is 2 divided by 4, or we can write 1 divided by 2. Okay? So this is easy. So now we can write here the probability function. What we need to do? We need to give to each possible value its probability. So I will do that. I will clean here this part. And I will write here the probability function. So what we do? The possible value 0, small x equal to 0, has probability 1 divided by 4. The value 1, x equal 1, has probability equal to 2 divided by 4. And the value 2 has probability 1 divided by 4. And then we put here 0 for all other real values that are different than 0 or 1 or 2. So when we write like O dot V dot other values. For the value of 0 we have this probability and so on, but for other values we put 0. Okay, but we can write this only with 3 branches instead of 4. Why? Because the values 0 and 2 both have the probability 1 divided by 4. So we can write the probability function in a shorter version. So we can put like here 1 divided by 4 is the probability of 0, but it is also the probability of 2. So we write x equal to 0, comma 2. The meaning is, this is not the decimal separator. The meaning is 0 has probability 1 divided by 4 and 2 also has probability 1 divided by 4. And now we put here 2 divided by 4 the probability of 1 and 0 the probability of other real numbers, other values. Okay? But let's put here another example where this procedure, the thing, what we have done here is even more important. And I will put the example of when we roll a dice. I will write now big Y, and big Y is the number obtained when we roll a dice. So I will put here the number obtained when we roll the dice. So if we can, possible values now are 1, 2, 3, 4, 5, and 6. And what are the probabilities? If it is a normal dice, the probabilities are equal to 1 divided by 6 for each of the values. So how I write the probability function is the small f of y, and now we can only use two branches because all the values, they have the same probability, 1 divided by 6. And so we can put 1 divided by 6. 1 divided by 6 is the probability of 1, 2, 3, 4, 5, and 6. And 0 for other values. It's much more easy to do this than put 1 divided by 6 for 1, 1 divided by 6 for 2, and so on. This is more short, okay? Now, let us give the definition of two very important parameters of random variables, the expected value and the variance. And they are very similar to what we have done in descriptive statistics with the mean and with the variance. Okay? So I will clean out this example, and I'm going to give here the definition of expected values. Expected value of a random variable big X. So, and we denote by the big E, and we put the name of the random variable between brackets. And what is the expected value? It's very simple. We multiply each value, each possible value, by the probability of the value. And we sum everything. So we do here a sum. And now I use this notation. What is the meaning? The meaning is all possible values. Okay, the meaning of this is all possible values. So in our first example, the possible values are 0, 1, and 2. Okay? And we do a sum between use here the products between probability of the value times the value. So let's do it with this example. So the expected value is equal to, we use the probability of 0 and we will multiply by 0, and so on. So we put here probability of 0 times 0 plus probability of 1 times 1 plus probability of 2 times 2. So this is very easy. Probability of 0 is 1 divided by 4 times 0. Probability of 1 is 2 divided by 4 times 1 plus probability of 2 is 1 divided by 4 times 2. So, and the result is equal to 1. This is easy to do. 1. So the expected value of the number of faces when we throw two coins is equal to 1. Okay. And now let's give another definition that are also very important, that is the variance of the random variable. So I will clean up this definition. I will put here the variance. Okay, the variance. So I will denote by VAR and between brackets the name of the random variable. And what is the variance? Now the variance is the expected value of the deviations squared. Deviations of the random variable from the expected value. So I write like this. Big E for an expected value of deviation of the random variable from the expected value and the deviation squared. So this is the definition of variance. But you already know the variance when we are dealing with the descriptive statistics. What is the variance? I can put S squared. When we are dealing with descriptive statistics, what we do? We sum the deviations of the values from the mean squared. So we sum here the deviations of the values from the mean, square it, and then we divide by n if we are dealing with a population, or by n minus 1 if we have a sample. But we are doing what here? It's a mean of what? Of the squared deviations. And here what we have? It's not a mean, but it's an expected value. We can also call mean instead of expected value. But I'm denoting here expected value of the squared deviation. Okay. Now we have different ways to calculate the variance. Here I will give now the most easy way. In the text that I will put today in the Moodle, I will put all ways to calculate the variance, and I explain why we use the following expression. So to calculate the variance, we can do the following. We can sum for all possible values the products between probabilities and the values squared. So the difference when we have done the expected value, we put here only the value. But for the variance, we put the value squared. But now we need to subtract the expected value squared. So let's calculate the variance for our example, so you can see that it is easy, not difficult. So I will put now here the definition of variance, and I will calculate using these two expressions. So I need to do the sum of what? Products between probabilities and values squared. So first value is 0, so I'll put probability of 0 times 0 squared. Second possible value is 1, so I put probability of 1 times 1 squared. And the last possible value is 2. I put here probability of 2 times 2 squared. And now I subtract what? Expected value squared. We already have calculated the expected value equal to 1. So here I will put 1 squared. And if you do all these calculations, you will get 0.5. But let me do one step. I will clean here the expression that we are using here to calculate the variance. So let me clean the theoretical expression. And now I will finish the calculation. So the probability of 0 is 1 divided by 4, then 0. 0 squared is 0. Plus probability of 1 is 2 divided by 4. 1 squared is 1. Now probability of 2 is 1 divided by 4. But now 2 squared is equal to 4. So now it's only to finish the calculations, and we will get 0.5. Okay, so the random variable number of faces when we throw 2 coins, the expected value is 1, and the variance is equal to 0.5. Okay? And now if you want the standard deviation, the standard deviation is the square root of 0.5. Okay? Now let me give you 3 properties for the expected value and 3 for the variance. There are more properties, but now I will only give to you 3. And the 3 are very important, and we will use them in exercises. So I'll put here properties of expected value. So properties of the expected value. So 3 properties. The first is for the expected value of a real number, a value. A real number is always the same, so we don't have any variation. Okay. So the expected value of k is equal to k. Oh, sorry. Here we are dealing with the expected value, not the variation. We will have another property for the variance, and the property is that the variance of k is 0. But now we are talking about the expected value of a number is equal to the number. Here k is a real number. Now the second is when we multiply a real number by a random variance. So is the expected value of k times big X. So we can put out of the expected value the real number, and we can write k times expected value of X. The third property is when we sum or subtract two random variables. So the expected value of X plus or minus big I is equal to expected value of X plus or minus expected value of big Y. So we can say that the expected value of the sum is equal to the sum of expected values, or we can use also subtraction instead of sum. So now the properties for the variance. Properties, of variance. So I will put here also 3. So, and the first is the variance of k. Variance of a real number is equal to 0, because we don't have variation. The number is always the same. Number 2, the variance of k times the random variable. Here, to put outside the variance the real number, we need to put it squared. So we put here k squared times the variance of x. So you see the difference? For the expected value, we put the k outside and we don't do more anything. We put outside. But for the variance, we move outside the variance the k, but we need to put the k squared. And the last property is for the sum or subtraction of random variables, x plus or minus y. And here we always get the sum, never the subtraction. Okay? We get variance of x plus variance of y. It's not correct to put here minus. If we have here variance of x minus y, we cannot do this. Why? Because if we do this, it is possible to have a negative value. If the variance of y is higher than variance of x, the result will be like negative, and that is impossible because the variance is equal to 0 or higher than 0. We cannot get a variance, a negative value for the variance. So here is always plus, even if we have here x minus y. It's easy to prove that. I will not do here, but it's not difficult to prove that. But this is true only if the random variables are independent. So if the x and y are independent. We will talk about the situation where they are not, about the case where they are not independent in other topic. But here we will assume always that x and y are independent, and we can do the variance of the sum equal to the sum of the variances. Okay? Now let's give the last concept of today's lesson, the distribution function. Okay? Now we will move on to the distribution function. Distribution function. We can also say, instead of distribution, we can say cumulative. Cumulative. So we can use both cumulative and distribution. And what is the distribution function? The relation between the distribution function and probability function is similar to the relation between relative frequencies and accumulated relative frequencies. I will put here one example to recall that. For example, when we talked about data grouped by distinct values, we gave the example of number of beds in apartments. And we put one example only with one example with only 4 possible values: the 0, the 1, the 2, and the 3. Okay. So now we have used relative frequencies, and we denoted relative frequencies by the small f. For example, let me put here some numbers: 0.3, 0.4, 0.2, and 0.1. So the sum is always equal to 1 of the relative frequencies. The same as we have with probabilities. The sum of probabilities are always equal to 1. But then we have done also the cumulative relative frequencies. So, and what we have done, for the first possible value we have the same. But now, for the second distinct value, here is not possible values. In the context of data grouped by distinct values, we denote these distinct values. When we go to the second distinct value, we sum the first two relative frequencies. We get here 0.7. When we move to the third, we sum the first 3 relative frequencies, so 0.9 and 1. So we are accumulating, we accumulate the relative frequencies. So and we do the same with the distribution function, because now the mathematical definition of distribution function is, I will denote by big F of the random variable x with a small x here, and the mathematical definition is probability that the random variable assumes a value equal or lower. So here we are using the words or lower. Okay, so we put not only equal, but equal or lower than the small x, and the small x can be any input. What we have done with the probability function? With the probability function, we put only the sign equal. Sign equal. With the distribution function, we put the sign equal, but also the sign lower. Okay? So we are doing what? We accumulate all the probabilities until the input in the distribution function. For example, if we are talking about our first example, the number of faces when we throw 2 coins. I can write, for example, small f of 1. What is the small f of 1? Is probability that we obtain 1 face. Okay, so it's probability that the big X is equal to 1. What is the probability? 2 divided by 4. But if we write the big F, the distribution function, instead of the probability function, if we write the big F, now it's not only equal, but it is also lower. So we write big X equal or lower than 1. And now, what is the probability accumulated until the value 1. The probability of 1 is 2 divided by 4. But lower than 1, we have the 0. So we need to add the probability of the 0. So this probability will be the small f of 0 plus the small f of 1. So it is 1 divided by 4 times 2 divided by 4 equal to 3 divided by 4. So the big F in 1 is equal to 3 divided by 4. The small f in 1 is only the probability that the big F is equal to 1 is 2 divided by 4. So not difficult, but let's now put the example of the dice. Number obtained when we roll a dice. So we can obtain 1, 2, 3, 4, 5, and 6. We already have written the probability function, but now I want the distribution function. So now it's important that you pay attention because we have some details when we write the distribution function. So now I will denote now the big X instead of big Y. I prefer to use the letter X. But now X is the number obtained when we roll the dice. Number obtained when we roll the dice. So we already know the probability function, but now I want the distribution, the big F. How we do that? So we start with the interval of values of values lower than the first possible. So the first possible here is 1. So I will write here that the probability accumulated until in any value that belongs to the interval of values lower than the first. So for x lower than 1, we don't have probabilities because it's impossible that we have it's impossible to have a number lower than 1 when we roll a dice. So we always do this with the distribution function. We put 0 for what? For values that are lower than the first possible. So here what we are doing here is for values that are lower than the first possible value. Okay. Then the first possible value. And now when we achieve the first possible value, what happened? We accumulate the first probability, the probability of the 1. So 1 divided by 6. But the output of the distribution function is 1 divided by 6 for all inputs between 1 and 2, excluding the 2. So for example, if I write the big F of 1.9, what is the meaning? The meaning is probability that the random variable assumes a value equal or lower than 1.9. What is the probability? It's impossible to get 1.9, but lower than 1.9 we can obtain the 1. And what is the probability? 1 divided by 6. So for all real numbers, I put here 1.9, but I can put any number in this interval. Any number between 1, including 1, and 2, excluding 2. I can put here, for example, 1.98. The response is also 1 divided by 6. Now, when we reach the next possible value, that is 2, what happened? Now we have the probability of the 2 and the 1. So and the accumulated probability is 2 divided by 6. And now it is 2 divided by 6, the output, when the input in the function is a number between 2 and 3. For example, if I put here 2.4, what is the probability that we get a number equal to 2.4 or lower when we roll the dice? 2.4, it's impossible. But lower than 2.4, we can obtain the 1 or the 2. And what is the probability that we obtain 1 or 2? The probability is 2 divided by 6. So now we continue this process until we reach the last possible value. Now we put here 3, between 3 and 4, and here we accumulate 3 divided by 6. Then when we reach the 4, we accumulate 4 divided by 6. When we reach 5, we accumulate 5 divided by 6. And when we put as input any real number equal to 6 or higher than 6, the accumulated probability is 1 for all inputs equal to 6 or higher than 6. For example, obtain a number equal or lower to 6, we know that we will obtain that because the possible values are 1, 2, 3, 4, 5, and 6. So its probability is 1. But the input in the function, I put 6, but I can put other number higher than 6. I can put here 10. What is the output? Of course, must be also 1, because we have 100% certainty that we will get a number lower than 10. We can put here 100. Any number above 6. Any number above 6. The output must be 1. Okay? So, now we always start with 0 for values that are lower than the first possible value. And we always finish with 1 for values that are equal or higher than the last possible value. So here we put the first possible, here we put the last possible value. Now let's finish today's lesson with only one example, and in this last example I will give you a theoretical distribution function. So let's put here the last example, and I will write a big F that is a theoretical example. So the distribution function in this last example will be, let me write here, 0 for x lower than 2. And then when we reach 2 and between 3, I will put here 0.4. So when we look to the distribution function, we know that the first possible value now is 2, because it's the value that we put here, 2. Now the second possible will be 3. And I accumulate here 0.9 of probability 0.9, and now I will put the last possible value and put here 5. And when we reach the last possible value, 5, and for values that are equal to the last possible, to a value that is equal or higher, I accumulate all the probabilities. So the meaning is that the last possible value is 5. Okay? But now the question here is, I gave you the distribution function, and the question is, what is the probability function? The question is, what is the probability function? And what is? We can obtain the probability function in different ways, but I will do that with the graphic of the distribution, because it's important to understand the graphic of the distribution function. And when we have a discrete random variable, we will have jumps, and the meaning of the jumps the meaning is very important. Okay? So I will start by drawing the graphic of the function. So how I do that? When we achieve the number 2, the output is 0.4. Before that, the output is 0. So I can write here here we have 0, then 1, but when we reach 2, I will put here an open ball. Why? Because the output of 2 is equal not to 0 but to 0.4. So we jump to 0.4. Okay. We jump to here. And now the output is 0.4 for all values in the interval between 2 and 3, excluding the 3. So I will put here what? I will put here a horizontal segment between 2 and 3. All values, they have all output 0.4. But when we reach the 3, I put here an open ball, because now the output of 3 is 0.9. So we have a jump from 0.4 to 0.9. So let me put here 0.5, 0.6, 7, 8, 9. Okay. Here is 0.9, and we jump from 0.4 to 0.9. And now, between 3 and 5, the output is always 0.9. So we have here a segment between 3 and 5. But when we reach 5, what happened? The output of 5 now is equal to 1. So we have a small jump here. When we reach 5, I put here an open ball, because the output of 5 is not 0.9, but it is 1. So close the ball here. We have here 1. In the horizontal, we are axis, in the vertical axis, we are putting here the accumulated probabilities. So is the output of the distribution function. So, but when we reach 5, the output is 1 for all values above 5. So this segment continues. The segment continues until infinity. Okay? But now, how we get the probability function is easy. The possible values are the values where we have jumps. So, where we have here jumps, we have a jump in number 2, we have a jump in number 3, and a jump in number 5. So, the possible values are values where we have jumps. So I can start writing the probability function, because I now know what are the possible values. The possible values are 2, 3, and 5. And what are the probabilities of those values? The probabilities are equal to the jumps. So, what is the jump? What jump we have in 2? We jump from 0 to 0.4. So, the jump here is equal to 0.4. Jump equal to 0.4. So, the probability of 2 is 0.4. Now, when we reach 3, we have another jump. And what is the jump? So we jump from 0.4 to 0.9. So the jump is equal to 0.9 minus 0.4 is equal to 0.5. So this jump is equal to the probability that the random variable assumes the value 3, 0.5. And the last jump is a very small jump. We have here, when we achieve the number 3, we jump from 0.9 to 1. So we have here a very small jump that is equal to 0.1. So 1 minus 0.9, the jump is 0.1. So now we have the 3 possible values where we have jumps. And we have the probabilities of those values. The probabilities are very simple to obtain, are equal to the jumps. Okay? Now I can put here 0 for other real numbers. So, and we obtained the probability function. So this is easy. Sometimes I ask you in the tests to do this, or you need to do this. For example, if you have only the distribution function and you need to calculate the variance, for example, to calculate the variance you need the probability function. So it's important to understand what we have done in this example. Okay? So let's finish now today's lesson. I will only talk a little about the concepts that we explained today. So we have talked about the discrete random variable. I think I didn't talk and I didn't explain what is discrete. I forgot to do that. I will do that now. Why we call discrete random variables? Because we can say, what is the first number that is possible, the second, and so on. And with continuous random variables, we cannot do that. Because continuous, they assume values in an interval of real numbers. But let me finish with that explanation. So, why we call this type of random variables discrete? What is a discrete random variable? Discrete random variable. We say that the discrete random variable assumes values from a discrete set. And a discrete set can be finite or infinite. Okay? But we can say what is the first, the second, and so on. So in a discrete set, we can put the elements of the set in correspondence with the natural numbers. So we can put the elements of the set in correspondence with the natural numbers. And this is very easy to understand. For example, in our first example, the possible values are 0, 1, and 2. And we can say, what is the first value? 0. What is the second? 1. What is the third value? 2. So we can put this in correspondence with natural numbers. We can do also the same with the example of the dice, when we roll the dice. But for example, if I put here the variable weight. Let me see if I can write this well. Weight. For example, weight. I can measure the weight of any student here. Or let's suppose I get 80 kilograms. 80 kilograms. Now, what is the next value? You can respond what is the next value. Here, after 0, we have 1. After 1, we have 2. But here, we cannot say what is the next value. If you put here 80.1, it's not the next value, because we can have, for example, between 80 and 80.1, we can have 80.01. Okay. So is this one? No. I can do the same. I can put another one in the middle, for example, 80.0001. And I can repeat this process always, can always repeat this. So there is not a number that is after 80. I cannot identify a number after 80. And these type of variables, they are not discrete, but they are continuous. But continuous random variables is the topic of the next lesson. So today we have talked about everything that are very important regarding discrete random variables. So I will finish now the lesson. I will end now the lesson. And then you can make some questions after I stop the recording.